All right, Chemistry 101, let's take a look at some problems from Chapter 4, and we'll start with this problem here, problem 4.103. It says, complete the following table for 3 of the naturally occurring isotopes of germanium, which is a metalloid that's used in semiconductors. So let's bring the table up here and let's figure this thing out. So we have 3 isotopes of germanium. We have germanium-70 in the first one. So this is germanium-70. Then we have germanium-73 and germanium-32. And the first thing it asks us for is for the atomic number. And since the identity of an atom is governed by the number of protons, which is the atomic number, and you can see that they all have an atomic number of 32. And so we can fill that in the first 3 boxes here, 32. And we can quickly skip ahead to the number of protons because the atomic number is going to be equal to the number of protons. Again, the number of protons is what gives an element its identity. The number of neutrons can give you a different isotope, but again, the number of protons governs the identity of the element. I'm going to go down to the last row here, which says the number of electrons. Since none of these isotopes have a charge, that means that the number of electrons should be equal to the number of protons. They should perfectly balance each other out. So that means all of these isotopes would have 32 electrons. Now the next thing we need to figure out is the mass number. And the mass number is the number of protons plus the number of neutrons. Protons plus the number of neutrons. And the mass number is found up here in the top left. And so we can just write each one of those down. We have germanium-70, germanium-73, and germanium-76. And that brings us to the last one, which is the number of neutrons. Now, we know the mass number, and we also know the number of protons. So in order to figure out the number of neutrons, we're just going to take the mass number, and we're going to subtract the number of protons. And we're just going to do this in our head. So if you look at the first one, I have 70, and I'm going to subtract 32. So 70 subtract 32 should give me 38. The next one, I have a mass number of 73. My atomic number, or my number of protons, is 32. 73 subtract 32 gives you 41. And then in the last one, 76 minus 32 gives you 44. And there you go. We've solved each one of these for the atomic number, the mass number, the number of protons, number of neutrons, and number of electrons. Question 4.108 says, indicate whether or not the following abbreviated orbital diagrams are possible and explain. When possible, indicate the element it represents. So right away, I can see there's a problem with this first electron configuration. The core electrons are helium, so that would be the 1s2 electrons that are left out. Then we have 2s, and we have 2 electrons. And you know that you can put 2 electrons in an s orbital, and they have to have opposite spins. So there's nothing wrong here. But when I get to my p orbitals, there are 3 types of p orbitals. Px, py, and pz is usually what we call them. And you can put 2 electrons in each one of these orbitals, but they have to have opposite spins. Now I've got a total of 1, 2, 3, 4, 5 electrons. So I would put them 1, 2, 3, 4, 5. So right away you can see what the big problem is, that you have 2 electrons that have the same spin, and that is impossible. Any 2 electrons in an orbital have to have opposite spins, just like you see in all of these orbitals that have 2 electrons. If we look at B, you see that we have 4s1 and 3d5. So that means we have a total of 6 valence electrons. And this element comes after argon. So if you count 6 electrons after argon, it goes potassium, calcium, scandium, titanium, vanadium, chromium. So chromium has 6 valence electrons. And normally if I was going to write them down, I would say 4s2, so we'll put 4s2, and 3d 1, 2, 3, 4, 5. And in the 3d, since chromium is element 24, I'd have 1, 2, 3, 4 electrons like that in my 3d orbitals. But what happens is one of these electrons gets promoted or moved into the 3d orbital. And the reason why is because, again, an electron from the 4s sublevel is promoted to the 3d sublevel to give added stability of a half-filled d sublevel. So again, this would represent chromium. Question 4.122 says complete the following table. So we'll start with potassium. The atomic symbol for potassium is the letter K, a little bit counterintuitive. Then it asks us for the number of protons. Well, for that, I just have to look at the atomic number. And potassium is element number 19 on the periodic table. Okay, and what am I looking for next is the number of electrons. Since this isn't an ion, the number of electrons should equal the number of protons. And therefore, I will have 19 electrons. And then lastly, on our atomic symbol, we want to put in the atomic number and the mass number, which is the sum of the number of protons and the number of neutrons. So 19 plus 22 gives us 41. So we'll put that in there. Next, we have element V, and V is vanadium. It's element number 23, so let's put that in, vanadium. Okay, and the number of protons is equal to the atomic number, which is shown here. So I have 23 protons. I should have 23 electrons because this is not an ion. And then finally, I want to figure out the number of neutrons. And I know that in order to calculate the number of neutrons, I take the mass number, and I subtract the number of protons. So 51 minus 23 gives me 28 for my number of neutrons. Next, we're not given the name of the element or the atomic symbol, but we know that it has 48 protons. And if I go to element 48 in the periodic table, that is cadmium. And so the atomic symbol for cadmium is CD, and then I'm going to put 48 down here for my atomic number. Now they've given me the number of neutrons, which is 64, and since mass number is equal to the number of protons and the number of neutrons added together, 48 plus 64 gives me 112, so I'll scribble that in there. And again, this is not an ion, so the number of electrons will equal the number of protons. Lastly, we have barium. The atomic symbol for barium is Ba. Then you go over to the periodic table and find barium, and it's element number 56, and the number of protons is what governs the identity of an element. So we'll put 56 for a number of protons, and we'll put that down here for our atomic number. They've given us the number of neutrons, and again, the mass number is equal to the number of protons plus the number of neutrons. So 56 plus 82 gives us 138. And again, since this is not an ion, the number of electrons should equal the number of protons and be 56. Let's take a look at question 4.128. It says name the element that corresponds to each of the following. So we'll start with A. We have an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. So that's a total of 24 electrons. And that would mean this must be chromium, because chromium has 24 electrons, and it doesn't say anything about an ion. It just tells us that we are looking for elements. In B, I have xenon, and then from xenon I go to 6s2. That takes me to barium, and then I go through the lanthanides, which is 4f14, then to 5d10, which takes me all the way through to mercury. And then I have 6p5. So when I go to 6p5, I get to astatine. So astatine, and the atomic symbol for astatine is At. It's in group 7A and has an electron configuration that ends with 6p5. Next, I'm looking for a halogen with the highest ionization energy. And you'll remember that ionization energy is the energy required to remove an electron from an element in the gas phase, and ionization energy decreases as we go down a group. As we go down the halogens, the ionization energy will decrease because the valence electrons get farther and farther away from that positively charged nucleus, and therefore they won't be held as tightly. So the smallest of the halogens, or the halogen that will have its electrons closest to the nucleus, would be fluorine. So fluorine is the halogen that will have the highest ionization energy. Next, I'm looking for the group 2A element with the smallest ionization energy. So if I look at group 2A, it goes beryllium, magnesium, calcium, strontium, barium, radium. These are the alkaline earths. And when we're talking about ionization energy, again, the bigger the element is, the smaller its ionization energy will be. So therefore, as we go down a group, ionization energy will decrease because the electron cloud gets bigger and bigger and bigger. And so the smallest ionization energy that will be found in group 2A will be that of radium. And lastly, I'm looking for the period 4 element that has the smallest atomic size. And what do we know about atomic size? We know that as we go across the periodic table, as we go up a group and go from left to right on the periodic table, the atomic size, we'll put here atomic size decreases. The elements actually get smaller. So if I look at period 4, it goes from potassium to calcium and so on and so forth to gallium, germanium, arsenic, selenium, bromine, and krypton. Krypton is the last element in the 4th period, and therefore it will be the smallest of all the 4th period elements. This question is kind of a fun one. It says, it's question 4.130. It says, of the elements potassium, so we've got potassium, calcium, bromine, and krypton, and I'm not listing them in any specific order here. It says, which one of these is a halogen? Well, the halogens are found in group 7A. They are fluorine, chlorine, bromine, and iodine. And so bromine is the halogen in this list. The next one says, which one of these elements has the smallest atomic size? And if you look at these elements, there's something that they all have in common, and that is that they're all in the 4th period. And the order they are in the 4th period is that first we have potassium, then calcium comes after that, then we go a ways over, then we have bromine, and then we have krypton. And so in terms of the smallest atomic size, as we discussed in the last question, we know that atomic size decreases as we go from left to right across the periodic table, and therefore krypton will have the smallest atomic size. The next question, C, asks us which one will have the lowest ionization energy. The one with the lowest ionization energy will be the one that is the biggest because the electrons will be the furthest away from the nucleus, and therefore potassium will be the element in this group with the lowest ionization energy. Ionization energy actually increases as we go across a period. The next one asks us which one will require the most energy to remove an electron. Well, the energy to remove an electron is the ionization energy. So basically we're looking for the element that has the highest ionization energy. And since I put the trend of ionization energy right here, we know that krypton is going to have the highest ionization energy because it's the smallest of all of these elements, and therefore the electrons are closer to the nucleus. It's harder to remove that negatively charged electron from the positively charged nucleus. And the last question just asks us which one is found in group 2A. If I look at the group numbers, potassium is in group 1A, calcium is in group 2A, bromine is in 7A, and krypton is in 8A. And so the answer, the one that's found in group 2A, is calcium.